Does it work?
Yep. I think everyone
so
can.
It works, yeah?
Yeah.
Okay, great. Thank you. Thanks for the invitation. Today, I will present some recent works that we've done in recommendation systems. And mainly these works are done by my graduate students, Nima and Sajjad, in collaboration with my colleague, Dr. Young-Lee Ren. And also, I should acknowledge Australian Research Council, which has supported our research through Discovery Program. So I'm not sure whether the audience is, they have done some research in recommendation systems. The first part of the talk will be mainly some introduction to recommendation systems, and the second part I'll just share you some of our research works. So you may have, I'm pretty sure that many of you have already experienced the recommendation systems. If you buy something from Amazon, if you buy on eBay, you may get some emails recommending some proper items that you might be interested in buying the same items. These methods, recommend algorithms, have been very good for many companies, and that their revenue is tightly linked with the recommendation process. For example, I've given some numbers here. 35% of purchases on Amazon is just because of recommendation. This is a $2 trillion company. 75% of what people watch on Netflix is because of recommendation. More than 60% of watch time on YouTube is because of the recommendation that Google gives you. 38% of Google News click-through is through recommendation. We have even a special conference within computer science community, Rexis, which is one of the top conferences in computer science, which is dedicated to recommendation systems. So this is outline of my talk. I'll talk some introductory things about recommendation systems, then how we evaluate recommenders. Then I'll talk a little bit about our user study, about precision diversity dilemma of recommendation systems. Then I'll present three recent developments of recommendation systems: a graph-based recommendation, similarity-based recommendation, negative ratings, and the recommendation. So I'll try to finish my talk in 35 minutes, something like that. Let's see how we go. If we don't have time, I may skip the last one, the negative ratings and recommendation. So this is the formal definition of recommendation systems. We have a set of users, you, and let's say we show items by I, and then we have some ratings, some existing ratings from users to items. And what we want is just to predict the utility function P from each user to some items that the user has not rated. And our objective is to learn P based on the past data. By past data, I mean the user item interaction data, the existing ratings, the existing clicks, that anything which has some sort of information about users and items and how they are interacting. And we will use P in our recommendation process. Many times we want to have a top-end recommendation. For example, we are looking for recommending 2 items to each target user, 10 items. What we do in that kind of cases, we obtain P for all items for each target user and then choose the top 10, top 2, or whatever we want. So recommendation systems are generally divided into 3 parts: collaborative filtering methods, which is the core topic today that we will see, content-based recommendation, and hybrid approaches, which is based on collaborative filtering and content-based. Again, collaborative filtering methods are divided into model-based and memory-based, and our work here will be memory-based collaborative filtering methods. So it's briefly, it is like this. So we do have some rating history for users and items. By the way, the collaborative filtering methods, which are divided into memory-based and model-based. Memory-based collaborative filtering methods are also divided by user-based and item-based. So for example, for a user-based method, which I have it, I have the process in this simple toy example in the figure. Let's say we want to recommend some books to one of these users. What we do, we first find similarity between these two users, and then let's say the left person is the most similar person to the right person, and then we look at the books that has been read by the left one and to recommend some of them to the right one, since they are similar, and it's likely that their preferences in the future will also be similar. So this is the general procedure for recommendation. First, we find the similarities between users. Then, for that based on that similarities for each target user, we obtain some the most similar users, which we call its neighborhood, and then we look at the items which has been rated by this neighborhood and select some for the recommendation. This is again a simple example of movie recommendation. Let's say we have 6 users, 6 movies. There are some existing ratings from users to some of these movies. For example, user 1, this person has rated 3 users, 3 movies, has given 2 to this movie, 4 to this one, and 5 to this one. So the recommendation problem is to consider one of these users, let's say this one, user number 5, as a target user, and then obtain P. These are the P values. So we run our recommendation algorithm. It gives us the values of these utility values, P. And then if we are looking for the top 2 recommendation, we choose this one and this one. Or if we are looking for the top 1, the best recommendation, only single item, we will recommend this movie to user 5. We do the same for all users. So this is the general procedure for memory-based collaborative filtering. Some recommendation systems are based on content-based filtering. There are many of these recommendations in the industry, since they don't need any interaction data. What we have here is just contextual information about users. For example, their age, their gender, location, their preferences, which has been provided by them. For example, some of users might have said that they like action movies, these sort of any contextual information that you might have from users. And similar information to items. For example, if we have movies, we might have the language of the movie, the location and country that the movie has been produced, the producer, a director, actors, its genre, whether it's an action movie or drama, these sort of things. And content-based filtering methods just match users to the items based on their contextual information. And of course, hybrid methods use both interaction data, collaborative filtering, plus contextual information. And naturally, these hybrid methods have better performance compared to either collaborative filtering or content-based filtering, since they use more data. But in many cases, we might not have any contextual data from other users or items. Users might not be willing to give any contextual data, and the only available solution would be to use, the only possible solution would be to use collaborative filtering methods, which are based on existing ratings from users to items. So again, here, I don't have that much math here. I've just included 2 pages of math. This is 1 page. The other one is just the evaluation metrics. This is a simple user-based collaborative filtering for the similarity. As I said, the first step in collaborative filtering is to obtain the similarity between users. Here I've used Pearson similarity, which I have a vector of rating for user a vector rating for user J, and I just compare these two vectors based on the Pearson similarity to obtain the similarity between these two users. I do the same for all users. So if I have, let's say, million user, I get a matrix 1 million by 1 million for the similarity of users, user similarity. And then I use these similarities for any user X and item Y, I obtain this value P, which is the prediction of the value of that item on this user based on the similarities that I have with my users. But there are tens of or even hundreds of ways to obtain the similarities. One might get similarity in other way, like cosine similarity, or one might get some improved similarities, or might play with the neighborhood in order to fine tune the similarity scores, in order to get rid of bad similarities, in order to strengthen good similarity values, and then use that improved similarity in the prediction process. So you might find different hundreds of methods for these sort of systems. So there are some challenges for recommendation systems, and I've included here some of the most important challenges of designing recommendation systems. One of the most important challenges is the data sparsity. We might have millions of users and millions of items, and if you consider this as a network, as a big network, a bipartite network, millions of users in one part and millions of items in the other part, among possible links from users to items, we have only few links. So we might have majority of links are missing. So the network representation of the recommendation problem will be heavily sparse, real recommendation systems. Scalability is also another problem. Cul-de-sacs is another problem. Attacks and precision novelty dilemma is also another problems, and challenges of recommendation systems. Here, I have some more information about these challenges. As I said, for the sparsity, in Netflix, for example, in the benchmark dataset of Netflix, which is a kind of benchmark dataset in many recommendation works, about 99% of the links are missing. So the data is heavily sparse. In another dataset, MovieLens, about 4% of the links exist, and more than 95% of the links are missing. So the network representation of the problem is heavily sparse. That makes our work a little bit tricky and difficult. Scalability is another problem. We have millions of users, and every day the number of users increase, the number of items increase. So our recommendation algorithms need to be scalable in order to accommodate increased number of users and items. Cul-de-sac problem is another very important challenge in recommendation systems. So if you have new users or new items without any rating history, or with just few rating histories, we will not be able to get any similarity for these new users or new items. Or if we get similarity based on existing few sparse ratings, that might not be a reliable similarity for that user item. That's why this is called as a cul-de-sac problem. Some users are cul-de-sac users, or some items are cul-de-sac items, and there are some solutions in the literature to address the cul-de-sac problem of recommendation systems. Recommendation systems, like many other systems, might have some attacks. For example, we might have hacker into our database, and then they might manipulate the rating of items, the ratings that users give to items, and these manipulated ratings will essentially, definitely will impact the outcome of a recommendation process. We need to have some algorithms that can detect these sort of attacks as well. So we have different evaluation metrics in order to evaluate recommendations. So this is generally, this is prediction problem. So we can use the existing methods, the existing evaluation criteria that has already been used for prediction problems, like mean absolute error, root mean absolute error, F1 measure, recall measure, precision. All these kind of things can be used for evaluating recommendation systems, but we can also use, or we should also use measures like catalog coverage, measures like diversity, novelty. In many cases, users would like to be recommended novel items. If you're using YouTube and every time YouTube gives you recommendation on popular items, popular movies, those that you've already seen, you don't like it. You usually you like to have some very novel, some items that you're not aware of, or some diverse items to be recommended to you. And this problem, but unfortunately, is not easy. So often if we want to increase the novelty and diversity means that we need to cover many items in the recommendation. In many cases, if we want to have highly accurate and highly precise recommendation systems, we might end up having only just few items in the recommendation. Let's say we have million items, but in order to have highly precise recommendation, we limit ourselves to, let's say, 10,000 items, and we ignore many items, which means this kind of recommendation is not novel. This kind of recommendation is not diverse. If you want to increase diversity of recommendation, the precision will go down. But in many cases, we need to make a trade-off between these two, and we need to have some algorithms that provides an option to make a trade-off between these two. Actually, we did a user study. I'll not go into the details of the user study. We did as part of our project. My student actually did this user study. We asked some participants, more than 200 participants. We had the data from more than 200 participants. Many of them were male. We had also some good number of female, and from different ranges. So what we got, we just recommended some items to them with high precision, or some items to them with high diversity, and then we analyzed what would be the impact of that recommendation. And what we found was that it's really depending on the users. For example, as you see here, in females, as the age of participants increased, they would like to be recommended items with more diversity. So we had clear differences between the genders. Males and females had different preferences for the evaluation kind of metric, and different age groups had also different different preferences for precision and diversity. This justifies our method, which was to have something with controllable level of diversity and precision. So we propose a method which gives an option to the system designer. By changing a simple parameter, they could play with the diversity and precision level. They could go from very highly precise recommendation to highly diverse recommendation. And I'm going to give you very briefly the details of this method. Again, I've kept all the mathematical settings of the method, and if you would like to know a little bit more about this, just please send an email to me, or I'm happy to get your questions after this. I'll share the draft of the paper with you as well. So we proposed a method called probabilistic graph-based method to solve the diversity precision dilemma in the recommendation process. It has 3 steps. We had rating transformation, and then we generated system state graph, and then finally we did the recommendation process. And I'm going to give you briefly details of these steps. So the rating transformation, usually items are given some rates from users, but these sort of rates, if you want to use exact ratings, that might look a little bit noisy. In order to smoothen the data, Usually recommendation systems just transform these ratings into 3, 4, 2 scales. Like in this case, we have transferred it into 2 scales, like and dislike. So if it is more than 2.5, the rating, which it means that the user has liked the item. If it is less than that, it means a dislike. After this, we construct a system state graph, which shows a graph between items. So this is, our method works by constructing a graph between items. That is a pretty simple process. So what we do, each item, here we have 5 items, 1, 2, 3, 4, 5, and each item might have 2 states, like or dislike. Users either like the item or dislike the item. So we have this graph. This graph has 10 nodes, 2 per item. And then we put a link between the items. For example, this means that we have one user who has liked item 1 and item 2, which is 1L, 2L, at the same time. It means that there is a link between 1L and 1.2 through this user. They have one user that has simultaneously liked these 2 items. We do the same for all. And these numbers, 2, 1, 3, it shows the number of users that have the same representation. For example, if we have 2 between 1D and 3D, it means that there are 2 users that has disliked item 1 and item 3 at the same time. When we have this graph, the next process, the next step is just to represent, to transfer this graph into 2 different graphs, one for likes, one for dislikes. So this graph, GL, is among the items that shows only the likes, and this shows only dislikes. And we just, again, denoise the data by ignoring the links between D's and L's. So then the next process would be just to merge these 2 in order to construct a graph. Our graph will be just a summation of this one and this one. So the strength of the link between 1D and 3D is 2, between 1 and 3L is 1. So between 1 and 3, item 1 and item 3, the strength of the link will be just 3, 2 plus 1. And we will use this matrix, this is a simple matrix, simple network between items in our recommendation process. And again, I show it by an example here. Let's say we consider user number 1 who has already liked items 1 and 2, and we want to recommend 2 more items to this user. So that our problem is top 2 recommendation. So the process is like this. We first construct this graph, the state graph, and then for each for the state graph, this is the items that has already been recommended, has already been liked by the users. These the user has already rated these items. So we look at the other items that have connections to this set. The items that have connections to this set are item number 3 and item number 4 and item number 5. So we get the top 2. The top 2 is item number 5 and item number 3, and then we get the one with the lowest weight, item number 5. This way, we control both diversity and the relevancy, which is the kind of precision of the algorithm. So we recommend, we recommend relevant and yet diverse items, or diverse yet relevant items. Then we consider, so the first recommendation will be item 5. Then we assume that the user has already rated these 3 items and do the same process, which will turn up, which will return item number 4 as the recommendation. So our recommendation will be item number 5 and item number 4. Our method has a parameter. Again, here I've skipped many details. The method has a parameter in order to choose these numbers. We call it tuning parameter. We call it beta here. By changing this parameter, which gives you options to choose different different items in that graph, in that simple graph, you can change the diversity and precision of the recommendation process. So here, this blue line shows the precision, and the red line shows diversity of the recommendations. And as you see, by changing this parameter, I go from highly accurate precision to very low precision, and from low diversity to very high diversity. So this gives an option to the system designer that that based on the population that it has, based on the users that it has, by changing the parameter, by changing this beta, can control the precision diversity level. For example, if they want somewhat precise, somewhat accurate, somewhat diverse, they can set the parameter to be like here. Or if they want highly precise, they can set this parameter to be here. Or if they want highly diverse and the precision is not that much important, they can change the parameter to some very close values to 1. By changing this parameter, they can control the diversity and precision level. So this was a snapshot of what Nima has done in his work. The other work that we have recently done, and that this work is under review, so it's not been published yet, is recommendation based on similarity prediction. So I've included here a block diagram, a simple block diagram of general collaborative filtering recommendation systems. So it has 3 steps. The first step is to create the similarity matrix between, let's say we are using using user-based similarity or user-based collaborative methods. So this will be user similarity matrix, and then for each target user, we will just consider a neighborhood which gives us the most similar users. Let's say the 10 most similar users, 20 most similar users. And again, that 10, 20, 30, 50 most similar users, that value is something that we can also optimize. And there are many existing works talking about that parameter, controlling that parameter. And then we do the recommendation based on the items that has already been rated by this neighborhood. What we have proposed here is to do rating, is to predict the trend of similarity. So for each 2 users, we do the similarity prediction. If their similarity is upwards, we correct the similarity, we strengthen the similarity, we improve the similarity. If their similarity is downwards, although they might be highly similar users, but our data might show that their similarity is downward, so we punish their similarity value and we give this improved similarity or enhanced similarity, or I should say updated similarity to our recommendation process. And by experiments, we showed that it is really important. So again, I'll give you a snapshot of the work here. Let's say we have 2 users. For this method, we need the time of the ratings as well. There are some benchmark data sets that they also include the time of the rating. For example, I've watched this movie and provided this rating at this particular day, or I've rated this product at this particular day. And we need that timing for this as well. So I need to know this item has been rated first, and then this and that and etc. So for each item, here I have different items. For each item, I know the rating of the item and the time that the user has rated that item. And then for each user, I construct a sequence of items and the times that and the rating. So the first time, let's say 0 or time 1, this user has rated this item, item 3, and has given 5 to that item. Then this has happened, then this has happened, etc. And the same for user 2. Then I do similarity prediction. So what I get, so for each of, let's say I fixed the user 2, I consider all the time scales of user 2, and then I consider a moving window of user 1. And first I consider 3 of the ratings, the first 3, and then the first 4, first 5, and until the end. And then I do the similarity prediction. So if I consider, let's say for this example, if I consider these 3, then the similarity between U1 and U2 at this time, the first step similarity would be 0. Then if I consider more snapshots of this user, I will have better similarity. If I consider all of that, I will have much better and improved similarity. So it means that these two users have upward similarities, and when time goes on, the similarity between these two users improves. And that means that if my target is user 2, user 1 is not only similar user to user 1, but also among the most similar users is an important one. So I have to further improve that similarity, or I have to further consider that user in my calculation. If on the other hand, if I have downward similarity, it means that that user is less important for the recommendation process, and I have to punish that in my methods. So existing methods do not consider this sort of similarity prediction. Our method considers, and if I have improved similarity, if I have upward similarity, I further strengthen my similarities and, in the updated form. And if I have downward similarity, I punish my similarities. I deduct something from my similarities. This can be used on any recommendation system. So on any recommendation system that is based on similarity estimation, regardless of the similarity method and regardless of the other steps of the algorithm, it can be applied as adds into the method. And we have applied it to many algorithms here, something like 15 algorithms. And this is the original precision. Here we've just studied the precision recall and F1 measure of the algorithm. We've not studied the diversity of the algorithm. If you look at this is the original algorithm. And for example, this is a Pearson correlation-based collaborative filtering. PCC is the original Pearson collaborative filtering, user-based collaborative filtering. This is the original precision. This is just this update. It gives about 40% improvement to the precision. We have some other algorithms that we have much less improvement, but almost on all algorithms that we applied this, we got some sort of improvement. In some cases, we have 60% even improvement. It doesn't increase the complexity, and that is just an adds-on to the similarity estimation process. Again, on other data sets, we have some improvements, less than the previous data set, but we have 11% improvement for the Pearson-based collaborative filtering. We have about 12% for item-based collaborative filtering, and etc. We have some sort of improvements in the method. So this is simple, but just some tweaks in the similarity estimation, we could improve almost all the algorithms that we have, we could consider. We could improve their performance, a broad range of algorithms that are based on similarity. And many many algorithms within the collaborative filtering space are based on the similarity estimation. The other piece of work which we are currently doing, and this is still under progress, and I don't have the complete information here, it's a nice work. There are some existing information in the literature which is suggesting that people behave differently to negative comments and positive comments. When they have positive comments on something, they tend to express it more. But when they are negative about something, usually they express it less than the case that they have positive comments. So let's say if I'm negative about the movie, in many cases I don't say it publicly, but if I'm positive about something, I would like to say it publicly. So we have many missing negative comments about the items from users. And this has been largely ignored in the design of recommendation process. Usually the recommendation systems, they consider negative comments and positive comments similarly. So you saw that in other previous cases, we had like and dislike, and we considered them sort of similarly. But there are, this suggests that this research suggests that there are many missing dislikes, which could be there potentially, but they are not there. We have to consider, or we have to reconstruct that, that kind of missing links as well. So we proposed a simple yet effective method. And as I said, this is still under progress. We hope that we can finish it up in the next 1 or 2 months. So what we did, we just proposed a recommendation which considers these negatives and positives separately. So we do the recommendation only based on negative comments. We do the recommendation only based on positive comments, and we somehow combine these two. So the existing methods put negative comments, positive comments, and then use them at the same time for their similarity estimation, and then building the recommendation. But here, we first use the negative comments separately, do the recommendation, use the positive comments separately, do the recommendation, and then somehow combine them. We are still working on the optimal combination of these two. And this is just a snapshot of our results. So you see that we have 4 cases here. The original algorithm, which treats them similarly, the negative comments, positive comments separately, and the combination of them when we do separately negative comments, separately positive comments, and combine them. And in many cases, the combined one works better. Again, this can be applied on any algorithm that is based on the collaborative filtering, that is based on similarity estimation. Broad range of algorithms are on that. Here we have applied it on 12 algorithms on good book data set. This is another benchmark data set. And as you see, we have improved performance here. Again, on another data set, again, the one that treats positive comments separately, negative comments separately, and then smartly combining them works better than definitely works better than the original, which treats them at the same time, treat them with the original algorithm. And it also works better than positive comments separately, negative comments individually. So I think that was my last slide about the contributions that we've made. Some brief concluding remarks. So there are many potential applications for REXIS in many different sectors, in e-commerce, in education, and very recently in digital health. There are many up and coming applications for recommendation systems. These systems have some problems, data sparsity and cold start problems, and there are many works in the literature that have been proposed to just tackle these problems. And there is a problem in the in designing recommendation systems, which is precision diversity dilemma. Here we propose a method in order to resolve this problem. And we also propose some methods based on some smart tweaks, some very tiny tweaks in the recommendation process in order to significantly improve their performance. There are some other works in the literature as well. Some of them have been done by our group. For example, social network-based recommendation. We might have links between users, social links between users. And we can use that kind of links in order to have better recommendation, or trust-based recommendation. We might have some implicit and explicit trust between users. We can get some help from that trust information to do better recommendation. And of course, deep learning methods, which sometimes, but not always, sometimes they are more effective, but we might overfit the problem, and we might have, although we might improve the precision, but if we look at the other measures like diversity and novelty, they are not that much good when we use deep learning kind of methods. And some advertisement here. This might not be relevant for some of you, but some of you might be interested in this. We are hiring 2 research fellows on a little bit different topic, on multi-objective optimization of battery storage systems. The positions are available immediately, and we would like to start the project within the next month or 2. And if you are interested in these positions, please send an email to me and we can discuss the opportunity. We are also hiring HDR opportunities. I'm the HDR coordinator of the discipline, so I'm talking about from that capacity here. School of Engineering, our school offers about 36K scholarship to both local and international students. If you know somebody from your colleagues, and if they are interested in doing degree in engineering from diverse field of engineering, electrical engineering. We cover within our discipline, we cover from electrical engineering to biomedical engineering to something like me, which I'm doing data analytics, machine learning applications. Please encourage them to contact me, and I'll help them to apply to our program. So I think this is the end of these slides, and I'll stop here and I'll take questions.
Thank you so much, Dr. Jalili. We actually have one question here in the comments.
Yeah.
I'll just read it to you. So what are some of the approaches to tackle the cold start problem?
Yeah, the cold start problem is for the case that we don't have enough ratings for users. We might have some new users or new items. One of the very effective methods that we have also a couple of papers on that is community identification. So if we have some new users, but we don't know the ratings for that new user, or the user doesn't have any rating, if we can assign the user to community of other users, not necessarily based on the ratings, but based on some other information, then we may get some help from the other users which are in the community of that user. Since they belong to the same community, they might have similar taste, and that kind of community-based recommendations might help to tackle the cold start problem. The other one was based on trust information. We have some recent works that we proposed a couple of new methods effective for cold start problem, and that was based on trust information. But sometimes we don't have that trust information, and we are blind, we can't do anything. If we have some trust information, that information can be used in order to just resolve the cold start problem. These are some examples, but there are many other methods as well.
Fantastic. I think that answers the question. We've got a couple more coming up in the chat here. Right. So we've got one question here on what kind of external information about users could help your recommendation system when you have both negative and positive feedback?
I'm not sure what you mean here, what kind of external information. So our work that I shared, the last piece of work, which was based on treating the negative comments and positive comments separately, that was based on only the interaction between users and items. So we didn't use any external information. We didn't use any contextual information about users, but definitely if we have some information about users, if you know their let's say location, education, gender, their taste. If we have a vector, a feature vector for each user saying this sort of information, that will definitely help, regardless of positive and negative comments. So that's a separate thing. To me, external information compared to our work is sort of separate thing, but that will definitely improve not only our method, but any other recommendation process. There's also one question about data set for cross-domain REXIS, which considers both social media data and user item interaction. Yeah, we've used some of these data. I don't have any data by myself. What we have used is just the benchmark data. One of them is just Wikipedia data. So that has both information about the user items and also about user uses. So in that data set, we do have trust information between users, which is kind of social relation between users. So I say that this editor is more trustworthy than the other editor, which is somehow a social relation. We can say that this is a kind of social information about users. That is available, and you can use that one as well.
Very interesting. I didn't know about that. Okay, we've got another question. Could you highlight the effect of COVID-19 pandemic on the data scientist jobs?
Yeah, this is a bit tricky. Definitely COVID-19 has impacted our business. So you're all within the university sector, and the university sector has been heavily impacted. So there will be less jobs in universities. That's for sure over the next 2-3 years, since universities are reshaping their business model, everything. And but I think there will be more and more jobs within the industry. So after COVID, not only data science, I think high-tech jobs like engineerings will also be in better position after COVID. So we are now relying on digital systems. So everything is going to be digital. Even our learning is on digital platforms, and they are based on lots of huge amount of data is created. And data science, I think, will become stronger after COVID. I'm part of a couple of CRCs. One of them is I'm not sure if you know anything about CRC. The CRC is Cooperative Research Centers. One of the recent CRCs is on digital health. This is a big program. So that's something like $60 million investment by the government. So CRC is a kind of a company which has many industries, and almost, I should say, more than 90% or close to 100% of the works involve data, but from the health sector. That is one of the sectors which is up and coming in data science. Similar to CRC in health, digital health, other sectors like energy sector, it is also heavily based on data analytics. And if you search for jobs in that sector, every day you see more and more data science related jobs in that sector. So personally, I believe after COVID, we will have a better job opportunities for high-tech jobs, including data science. But this might be not next month, but definitely within 5 to 6 months, I expect to see improved job market.
As I say, every cloud has a silver lining. Okay.
Pardon?
Every cloud has a silver lining. So what? One more question here. What's your opinion about using multi-armed bandits as part of recommendation systems?
I don't know anything about multi-armed bandits. Can you help me to know a little bit more about that? What is that?
I'm not sure myself.
I can Google it to see what is.
I believe it's a sort of algorithm, but that's just a blind guess.
So I'm reading from Wikipedia. In probability theory, the multi-armed bandit problem is a problem in which a fixed limited set of resources must be allocated between competing choices in a way that maximizes their expected gain. We have a rather old work, not on this name. I didn't know this term actually. It seems that's a specialty term in statistics, but we have a work, I believe it is in 2014. We have proposed a recommendation based on resource allocation. And I believe that is pretty similar to what this problem is talking. That problem, resource allocation is a well-defined problem in communication systems, and we use that concepts in order to build our recommendation. But that is pretty old. It's 6-7 years ago, and I believe the recent state-of-the-art methods they perform much better than that.
Right. Thank you for that answer. I actually have a couple of answers on my part, if that's okay. Are there any issues concerning privacy? And what I mean by that is that users may not necessarily know, they're not necessarily aware that their online choices are being stored somewhere, and maybe some people will object to that.
Oh, yeah, this is a big thing. So the privacy, you might have heard that we have a Netflix competition about 10 years ago. And one of the benchmarks that we have in recommendation systems, and if you look at the recommendation papers, almost, I should say more than 80% of them are based on Netflix dataset or use Netflix in their comparison. But that was based on blind dataset. But then there were some works that they could recover the identity of users based on that blind dataset. And after that, Netflix just remove the data set. They are not publicly available through the Netflix. Some people, they just share the data set, but it's not official from Netflix. That's always an issue. You can always de-identify the users, and if you give some brief information, you can always link it to the data set and then de-identify the users. That's a critical information. And I believe many communities are working on that privacy issues. It's not my expertise, so I don't have any active line of research in privacy, but that is clearly one of the issues that not only in this case, but in any other data science related projects that you need to consider. For example, in digital health related projects, you have very critical information about the health of patients, and this is super critical. So the privacy is really important. And but as I said, I don't work on that field as an active researcher, so I might not give you some good answers. But that is definitely one of the concerns in these kind of projects.
Yeah, that's a fair comment. Okay, we've got one more question from the audience. Do you work on natural language processing combined with recommendation systems?
No, I don't work on that. That is part of the content-based recommendation. So it means that when you have some content about items, so you dig that content and then you produce some information about that item. I have not, I'm not expert in NLP kind of thing, and I've not worked on that. The only works that we've done in the recommendation systems on collaborative filtering, where we have a network. So I'm basically a network scientist. So my really research expertise is modeling phenomena like networks, and That's why we've considered only the rating information, which is a kind of network between users and items, and we want just to complete the network.
Right.
But there are definitely some works on, and NLP has definitely some applications in the recommendation process.
Right, right. I've got one more question. One of the challenges you mentioned at the beginning of the talk is sparsity. So my question is that because most of the users don't leave ratings? My experience is that most people don't really bother to leave any ratings when they do something online.
Yeah,
is that the reason?
Yeah, definitely. That might be the reason. Or we might have a totally new user without any kind of experience in using the item. So you might have a completely new user to the system without any rating, or just few ratings. You might have some few ratings, but the similarities based on that few ratings might not be reliable. Again, that user is some sort of cold start user. So in many works that they are studying cold start problems, what they do, they just set a threshold and then they vary that threshold to see if I consider only users with more than, let's say, 10 ratings, what would happen. If I consider users with more than 20 ratings, what would happen. But that might be one of the reasons. But what the Yahoo research has found is that when you have negative comment, you're less likely to express that comment compared to the positive comment.
There's also this issue of if I know that but my actions are anonymous on a website, I'm more likely to do something and leave a comment or leave a rating than if I know I can be identified.
Yeah, that's a good thing. But if the ratings are anonymous, what we can do, we can get some general idea or consensus about the items. But if it is anonymous, we can't link it to any user. So that might help us, but to some extent. But since we don't know the user, we can't link it to the existing user. But that will definitely say something general about the items, which definitely we can use it to improve our recommendation.
Or I suppose it's possible that the situation is not symmetric, where you are anonymous as far as the other people are concerned, but for the database, the database users know who has left what comment.
Definitely.
Yeah.
Definitely. They might get your IPs and that's sort of the device that you're using.
Yeah.
Even if you use the same device with different IDs, they might get you the same sort of user tag. And definitely they do these sort of things. Otherwise, they couldn't do any recommendation. And they use all these sort of different things in order to identify the users and then base their algorithm on that.
Okay, hold on. We've got one more question. I think we're going to take that last question and then we'll have to stop because we're running out of time.
Yeah.
Okay, so as a part of the way you explain to build the graph of likes and dislikes, is discarding edges between like and dislike nodes. What kind of information those edges show that we remove them?
This is the kind of interesting thing, but we wanted to just denoise our data set, and we thought that that could be kind of a noise to our system. So we are mainly interested in this work. We were mainly interested in just a graph of just likes and just dislikes. We have another work, but that's also an old work. It is somehow related to this, but not exactly. There, our method was based on Markov chain, and there we didn't do like that. So we could even have a transition from like to dislike and from dislike to like, but it had some limitation as well. So it was pretty complex and we couldn't apply it to large graphs, but this method is really applicable to large graphs. But to have a direct answer to this, we've not explored it in detail. So the kind of really information that they are providing from like to dislike, definitely they provide some information, but we've not explored that.
Yeah. It just shows that there's so much more research that needs to be done in that area. So if anyone of you is interested, please feel free to contact.
Yeah, definitely. As I said, there is a specialty conference for Rexis.
Yeah.
The name of the conference is Rexis. ACM Rexis is one of the top conferences in computer science, and every year there are 300, 400 papers just in that conference about recommendation systems. Apart from that, in all top computer science conferences like KDD, WWW, on a yearly basis, we have more and more recommendation papers. So the field is, I think, it's one of the hot fields within computer science, and also somehow within network scientists as well. There are some physicists who are working on recommendation problems, but from different perspectives.
Right. Well, so I think we can stop here. Thank you so much, Dr. Jalili, for spending the time to share your expertise with us. We really appreciate that.
My pleasure, and thanks for the invitation.
No worries. So yeah, let me stop the recording here.